Welcome to 2.4 Rates of Change into Tangent Lines. Okay, so we want to go ahead and talk about average rate of change. We want to be careful not to always think of everything that we don't want to think of a speed every time we hear of rate. Okay, we want to also be able to think of how things change. It could be how potential energy changes as a spring is compressed. Anytime there's an independent variable and there's a change in the function value, we might be interested in an average amount of change over a given amount of something. It doesn't even have to be time. So, just in general, we're interested in amount of change divided by length of interval. So it might be distance over time, which is speed, but it could be other things too. Okay, for example, we could say find the average rate of change of f of x equals x cubed minus x over the interval 1, 3. Okay, it needs to be a closed interval here. So basically we have a certain amount of change in the function. So the function will change from being f1 to being f3. So the difference will be f3 minus f1. And the length of the interval would be 3 minus 1. So this would be the average rate of change. Okay. The f of 3 and the f of 1 have to actually be evaluated. So for that we're going to be using 3 cubed minus 3 minus 1 cubed minus 1. And then the length of the interval is just the difference in the two x values. These are often referred to as a and b, by the way. Okay, so this is 27 minus 3, which is 24, and that's 1 minus 1, which is 0. And then down here we have 2, so the answer is 12. The units will be determined by the ratio of whatever the y-axis units are over the x-axis units. Okay, it's also important to understand that this is also the slope of the secant line. Parentheses there. Secant meaning it touches both points on the curve. Touches, it literally means touches more than one, or cuts the curve. But it's passing through the 2 points. It passes through one comma f of 1 and 3 comma f of 3. Okay, so 1 comma f of 1 is just the point 1 comma 0. And 3 comma f of 3 is the point 3 comma 24. Alright, so if you can picture this, there's a point right there, and we have over here a 3 way up here at 24. The curve connects these 2 points. And the line that we're dealing with is tangent, or excuse me, is secant to these two. So we're talking about a line which runs from here through here. And we just found the slope of that line. Alright, so for our next example, we are going to just jump in and look at a homework problem. It's actually similar to one of the homework problems. This is number 8 from page 92. Okay, so the scenario is there's a diagram given, and I'm going to just go ahead and paste it in. So for my example, I'm going to cheat here and drop the graph in that they gave us in the book. Don't worry, I do want you to copy it, but you don't have to copy every little bit of it. We'll just write down the coordinates. How's that? Okay. Okay. So the scenario is that somebody has dropped a wrench from the top platform of a communication mast on the moon. Okay, so somebody's on the moon. Anyway, they dropped this wrench, and we have distance fallen and elapsed time. Now, we saw a problem like this recently, but it was given a given function, which is y equals 16t squared, and that was distance fallen in feet, right? Not meters, and it was seconds, if you remember. Now we're on the moon, so if this were the Earth, this would be 9.8. It would actually be y equals 4.9 t squared, which is half of 9.8. But we're on the moon, so things are different. We're not using 9.8. We're using approximately, I believe it's 1.6. I need to check that, but I'm pretty sure it's 1.6 for the moon. Okay, so they titled this problem Lunar Data. Okay, well, ultimately what we're trying to do is we're trying to look at the various points here. We're going to be finding slopes of lines. So we're interested first in the line that connects Q1 to P. And then we're interested in the line that connects from Q2 to P, and then Q3 to P, and Q4 to P, and so on. Okay? So those are going to represent different lines. So that one, I'm interested in that one. Okay, and then we're going to be looking at that one. And then we're going to be looking at that one. And we're going to be looking at that one. I'm going to be looking at the various slopes. That's what we're trying to do. Ultimately, we're really interested in the actual slope at P, which is a little bit different concept. That's the slope of a tangent line, a line that touches only P and doesn't touch any of the rest of the curve. Okay, but that's sort of the notion, the next notion, the tangent lines notion, that's coming up later in the lesson. Okay, so first thing I always recommend that you do is, I really recommend this. You want to take a look at your axes, and you want to go ahead and just put your pencil right there and take note of the units. Think of what's going on there and here. You want to pay close attention. Okay, the units are meters and seconds. Okay, this tells me something. This tells me that if I at any point need to divide these two quantities, I would be looking at a speed. And we know that when you are doing slope, you are doing exactly that. You're doing rise and run. So rise over run, that is slope, is in fact meters per second. Interesting. Okay, so it is important that whenever you are given a graph, take a look at the units on the y-axis. Maybe mark it there, touch it at least with your pencil. Take a look at your x-axis, mark there, and remind yourself what it would mean for you to do a slope for that graph. It would turn out to be units of meters per second, and then that could be understood to mean speed, right? Speed. Okay, so we know what slope is going to mean. Alright. Maybe that was already obvious to you. Alright, I'm going to go ahead and shrink this down so we can have a little extra space. Alright, let's write in what we think these points are. Now, I didn't actually measure these, but I'm pretty sure that Q1 is located at 5, 20. So and I would probably suggest that Q2 is probably about 7, maybe 38, and that Q3 is at 8.5, 56, and then Q4 is at 10, 80. No, I'm sorry. What am I saying? This is 56, and then I'd say Q4 is at 9.5, 70. At first I thought it was 71, but I looked at the book, it's actually 72. Okay, so just do your best with that. The goal is, and point P is at 1080. Okay, the goal is to find the slope of the various lines from point Q1 to P. So that slope would represent the average speed between the 5th and 10th second. Alright. And then from Q2 to P, that'd be between 8th and the 7th and the 10th second, and so on. And then from here to here. Oops. And then lastly from here to here. Okay. Yeah, so we're going from Q1 to P, Q2 to P, Q3 to P, and Q4 to P. Okay, actually the ultimate goal is to take a look at a line that might be, say, tangent to point P. So tangent, remember from geometry, means touching once. Touching once. So I wonder what the slope of that line is. We're going to have trouble with that one. That's our final topic here. We're not going to be able to find the exact slope of it without calculus. But it is true that the lines that we're doing, if we do them in that order, they are getting steeper and steeper. And so let's start with this one. Alright, so let's work it out real quick. So all we have to do is take the slope of line PQ1 by taking the rise over the run. So we're doing this one and this one, right? So 80 minus 20 over 10 minus 5. Alright, so that's 60 over 5, which is 12. Alright, and then we'll do PQ2, which is basically this line. Notice it's steeper. Okay, so this is we're no longer looking at those. We're looking at Q2 and P, so it's going to be 80 minus 38 over 10 minus 7, over 3. 42 over 3, which is 14. Okay, and then PQ3 is 80 minus 56 over 10 minus 8.5, which turns out to be 24 over 1.5. Let me double top and bottom there. 48 over 3. And then we'll do PQ4, which is 80 minus 72. Over 10 minus 9.5. Okay, so 8 over 0.5 multiplied by 2 here, just to, so we can do it in our head a little easier. 16. Okay, so the answers are 12, 14, 16, 16. Okay, so for our lines, basically we're looking at I'll just move this one. Oh, by the way, the guy who taught us, who gave us the notion of moving these and looking at them in consecutive, sort of an animated way, was Fermat, very famous mathematician, 17th century. Okay, well, it's in the book, you can read. Yeah, so basically this is the first one we did, and then the second one we did was this, and the third one was this, and then we did this one. And you can see that these have gotten steeper, and our ultimate goal was to do one that was tangent, and so we're actually not far off, right? So we're actually not very far off with our slope. How are we doing this thing eventually? Trying to get that tangent line slope right there. So the last one we did was the most accurate of the batch. And you can see that actually the values kind of stopped changing. We've got 16 here. No, it's actually not 16, probably. It's probably steeper than that. But we're going to go with 16. So the slope of the tangent line is approximately 16. Okay, we should probably take a moment and talk about what these units are. This might be the most important part of the problem. Okay, anytime you're given a graph, take a quick note of your units. Now, there are two things you do with units on the x and y axes. One is you divide them, which is what you're doing basically when you're finding a slope. You're doing the rise over the run. So our units are meters on the y-axis and seconds on the x-axis. You always want to set this up. You want to do a ratio and a product. A ratio and a product. Given a graph, you look at the two types of units you're dealing with. Imagine what it would be if you were to divide them. It would be meters per second. And if you multiply them, it would be meters times second. Okay, well this is very meaningful. This is speed. And meters times second, well, that might not mean much to you. So, but what we do see is that anytime that we have a distance and a time, that the slope represents speed. So this is something we usually do. Okay, so we should really go back and put meters per second on all of these. and that's the approximate speed of the wrench after the 10th second of falling. So that is some tall tower. It's been falling for 10 seconds. On the Earth, it would have gone further in 10 seconds. So it probably would hit the ground, I guess. Okay. And just as a reminder, don't forget to go back and put in the units. It was meters per second, remember, because we're doing rise over run, and the y's over x's and these are meters per second, and of course represents speed. Okay, so after the 10th second, this thing is falling at approximately 16 meters per second towards the surface of the moon, and if this had been on Earth, then after 10 seconds it would be moving quite a bit faster. Finding the slope. And tangent line. Okay, so we're going to go ahead and insert a graph here. Of a parabola. Okay, so we're just going to go with the example they have in the book here. Example 3. Find the slope of y equals x squared at 2, 4, then find the equation of the tangent line. Okay, so our parabola should look like, pass through here, here, 2, 4, and then it goes up pretty quickly there. We have the left side as well. Alright, so we're interested in this point here. Interested in constructing a tangent line there as best we can. I don't know why it just came up with I don't know about that. Okay, trying to get the slope of that tangent line. To expect us to draw a tangent line. Okay, so to do that, what we're going to do is we're going to go ahead and let's suppose there's another point over here. Let's say right there. And this point will be, since this is the point 2, 4, we'll call this the point 2 plus h, comma, and then 2 plus h squared. Any point on this graph has the same features that the x-coordinate once squared is your y-coordinate. So this is the correct relationship between your x and y in all cases. So there's some kind of a horizontal separation between the first point I drew and the second point that I drew. But we can go ahead and find the slope of that line that connects them. Okay, now that's not a tangent line, but we're going to fix that in a minute. Okay, so the slope of the secant line is, again, that is y2 minus y1 over x2 minus x1. Okay, so the numerator turns out to be 4 plus 4h plus h squared minus 4 . sign this someday. I guess I have to take a class in it or something. Okay, and then on the bottom, h. Okay, and then we can see that these cancel out, right? And we can factor out the h on top. And these cancel out. Leaves us with 4 plus h. So the 4 plus h is the slope of that tangent line. Okay, good to know. Okay, we were actually more interested in not a tangent line, or not a, I'm sorry, I think I said this is a tangent line slope. This is the slope of the secant line that connects those 2 points. Okay, we're really more interested in just the point 2,4. So how can we eliminate that gap there? So what we're going to do is going to take a limit. So we will let h shrink to 0. This brings the point 2 plus h comma 2 plus h squared right onto the point 2 comma 4. Okay, so we're going to go ahead and do a limit. H goes to 0. And we get 4. Okay, this is a big deal. We just found the slope of that line that's tangent. Oops. I barely even draw that thing. Whoa, I just went the whole crap. This line here has slope 4. Okay. I wonder what the equation is. Knowing that it has a slope 4 does tell us something, but it would be nice to know what the y-intercept is for that. Okay, so to get the equation of the line, we can use, okay, this is my favorite, y minus y1 equals m times x minus x1. Okay, so let's plug in the 0.24. So we know it has slope. Let's go back up and look. Oops. We know that it has slope 4. And that it passes through 2,4. That's plenty of information to find the equation of the line. Okay, so let's go down here. It has slope 4 and passes through 2,4. So we could put in y minus y1 equals m times x minus x1. This is x1 and y1. Sorry about the jumping there. This is the slope. I'm sorry, we're going to put in the values. So we put in 2 there. Okay, so y minus 4 equals 4x minus 8. Y is equal to 4x minus 4. if you add the 4. You can kind of see that if you go back to where I was, I could actually, now that I kind of know that, now that I do know that equation, I can actually put that line right as it should be, give it the right slope there. Let's see. It's got to pass through 4 down here. Okay, so it's got to have slope 4. Yeah, bingo. Okay, so what you can see is my problem, my original problem wasn't drawn properly. It wasn't drawn where it was. A little too wide or something. Okay, so there it is. That's huge. So that's one of the most important topics. That limit as h goes to 0. One of the most important things you could have learned for today.